In this video, we're going to talk about complex zeros and the fundamental theorem of algebra. So let's start with a little recap of complex numbers. So complex numbers are written in this format, where I have a, which is a real number, plus bi, which is an imaginary unit. So b is some number, some constant, and I is our imaginary unit. So it will always have an I in it. So as a refresher, I is represented by the square root of -1. If I square I get -1. If I cube it, I get -I, and if I bring it to the fourth power, I get 1. I to the fourth is my favorite one. Ha ha. See what I did there? Love it. Can a complex number just be an imaginary number? So if this was 0, could I just have like 5i? Of course. Could your complex number just have a real component and no imaginary component? Yes. So technically, real numbers are also complex numbers, but they're not often referred to as complex numbers. And just in case you were wondering, graphically, we can graph complex numbers in the complex number plane, where our x-axis is transformed into the real number axis, and our y-axis, you guessed it, is the imaginary axis. So whatever that point is in space, that a plus bi, it's more like a vector in a 2D space with a direction and a point there. But we will be graphing complex numbers. I just wanted to show you because I think it's cool. So what we have here, this is a formal definition of what a complex polynomial function looks like. So, and that contains complex variables. That is all to say what the fundamental theorem of algebra says, which is that every complex polynomial function, f of x, that has a degree of 1 or greater has at least one complex zero. And that's all to say that every polynomial function can be factored, and they may have all real zeros. They may have all complex zeros, or they may have some combination of both, but we can factor every polynomial using complex numbers if they don't have real zeros. That's what I'm getting at here. And what helps us do that, in part, is the conjugate pairs theorem. So what that says is that if I have a polynomial function whose coefficients are real numbers, that if a plus bi, remember that's the definition of a complex number, is a 0 of f, which is a factor, the complex conjugate, so r with that bar over it, is a minus bi. So you keep the a and the bi the same, you just switch the sign between them. So let's use that idea in an example. So let's say I have a polynomial function of a degree 5 whose coefficients are real numbers. So it has zeros of 1, 5i, and 1 plus I. Let's find the remaining 2 zeros. So first I need to identify what my complex roots are, or my complex factors, and then figure out what their conjugate is going to be. So 1 is a real number. -1 is not going to be the conjugate pair to that, unfortunately. But 5i is complex because it has an imaginary part. So I would rewrite that as 0 plus 5i, and then its conjugate pair is 0 minus 5i. So -5i is another factor. And then I have 1 plus I, which is a complex number. And if it's 1 plus I, its conjugate pair is 1 minus I. So -5i and 1 minus I are the other 2 zeros. They're not real completely, but they are factors, which is what the fundamental theorem of algebra is trying to say. We can find all the factors, real or imaginary or both. Let's work through another example. So let's find a polynomial function, f, of degree 4, whose coefficients are real numbers, that have zeros 1, 1, which tells me a lot about its multiplicity, and -4 plus I. So I start my equation, f of x, and it's equal to a, so there could be some numerical value out here. You could place it with whatever number you want. I have 2 zeros that are the same, so 1, so that becomes x minus 1, all squared. They gave me this 0, so it would be x minus the quantity of negative 4 plus I, which you can simplify if you want to. And then, because this is a complex zero with a real and imaginary part, I can find the conjugate pair easy peasy. So it's the same, start as this, x minus negative 4, but instead of plus I, it'll be minus I. And could leave it here in full factored form, or we can distribute our negatives, combine all our like terms, FOIL it, but this is good enough for me. All right, one last example. So let's find the complex zeros of the polynomial function. So this is where you're given the function, but you're not given any of the zeros, and you're asked to find them. So I'm going to graph it. And in graphing it, I find two real zeros. I have negative 2. It crosses through, so that tells me it has an odd multiplicity, so 1 or 3, but more likely 1, because there's another 0 that also crosses, so 1/3, and that has to be at least 1. So 1 plus 1 makes 2. I'm looking for up to 4. So these won't have multiplicities of 3 each. One could be 3, the other could be 1, but the way to do that is with synthetic division. So as a reminder, we bring down all the coefficients in order and always check that we're not missing any exponents. So 4, 3, 2, 1, 0, perfect. Don't need to put a 0 in here. So I put my first factor in here, negative 2, and then I find all of these numbers and a 0 remainder, which is a good sign. And so if I divide this function by x plus 2, I'm going to get a cubic. So I'm going to take this cubic and divide it by 1/3 to see what my remaining x squared equation is going to be. See if I can factor it. Probably not, but we're going to find it. So I put the coefficients in green right here. I'm going to divide by 1/3, which is the other factor I found when graphing, and luckily that 1/3 is pretty easy to work with. Get a 0 remainder. So that leaves me with 3x squared plus 0x plus 27, which I could take a 3 out of and get x squared plus 9. We can't factor that. Those will give us complex zeros, so I found the other two. So these will both be multiplicities of 1. So in factored form, it would be x plus 2 to the first, x minus 1/3 to the first, and then 3 times x squared plus 9. But if we're looking for the complex zeros, I would have 2 of them already, negative 2 and 1/3. And then what I do to find the last 2 is I would set my factor. So it could be 3 times x squared plus 9, but it would end up just being x squared plus 9 is equal to 0. Solve that down, and I get x squared is equal to negative 9. Take the square root. X is equal to plus or minus, because right, we have to consider both forms, is equal to plus or minus square root of negative 9. You can break that down into the square root of negative 1 and square root of positive 9. Square root of 9 is 3. Square root of negative 1 is I. So the other two complex zeros are positive and negative 3i. And that's going to do it for this video. Thanks so much for watching.